Hello, hello. In this video, we're going to be talking about linear functions. That's our topic of this lecture. You are familiar with linear equations, but I will briefly remind you what you already know. So linear equation looks like this. The general form is y equals mx plus b. There are other forms as well, of course, but this is called the slope-intercept form because m, that's the constant in front of x, represents the slope of the line, and b is the y-intercept, or the point where your line crosses the y-axis. Now, if we substitute now, when we know about function and function notation, we can rewrite the same equation in a function form. So to do that, you just substitute y with f of x, and the rest is the same. So this is the nature, this equation, this is the nature of the relationship between x and the y. This is knowing x, that's how you calculate the y, that's the rule of the function. And this notation tells us that x is our independent variable, or our domain, our input value, and the output is calculated based on this rule. Calculation. And but if I gave you let me give you an example. Let's say we have f of x that's equals 2x minus 1. So how would you graph it? Well, if we knew nothing about what this might look like, then, and it applies to any function that you don't know what it looks like, what you do is you create a table of values, right? So we are gonna get some x values and f of x. Calculate the f of x values based on that x value. So let's start with a 0, for example. We plug it in, we get 2 times 0 minus 1 is negative 1. So our y value, or function value, is negative 1. And then when our x is, let's say, positive 1, we have to plug it in. So we're going to say f of 1 equals, and then follow the rule. So that's 2 minus 1 is positive 1. And we could calculate one more value. Let's take a negative 2, for example. So f of negative 2, when the function value when x is negative 2, will be 2 times negative 2 minus 1 equals, that's a negative 4 minus 1 is negative 5. So, and if you remember anything about linear functions, the graph of this function is a line. Graph is a straight line. I'm just gonna say a line. And in order, and 2 points define a line. So in order to graph a line, we only need 2 points. And I always recommend 3 or more, just to check your work, because if you made an error on one of the calculations, then if your points don't line up, then you know you made a mistake. But if you have only 2 points and you made a mistake on one of them, then you don't know that you made a mistake. Okay, so a nice way to check yourself is to have more than 2 points. Now, So we know that f of x stands for y, so we have ordered pairs now, 0, -1, and then 1, 1, and -2, 5, and then you go ahead and put those points on the graphing paper on the coordinate system. So just wanted to mention that this is our basic graphing technique. Um, of course, you probably know other techniques, other methods to graph your linear function, and we'll go over those in a little bit. But if you're later in this course, you will be asked to graph different functions, and some of them you haven't seen before. So if you're looking at an equation and you're thinking, gosh, I don't know what this is going to look like, then this is the technique that you fall back onto. You make a table of values for that function, plot the points, and see what it looks like. So here's my scale or Cartesian coordinate system, and I'm going to plot those points, 0 and -1. That's our intercept. This is the point on the y-axis, so it's a y-intercept, and the x-coordinate there is always 0 for the y-intercept. Now the next point is 1, 1, and -2, -5. Where's my -5? Right here. Okay, it looks like my points line up, so we can now use a ruler to graph that line. There you go. And this is f of x, which is 2x minus 1. As we mentioned before, this b, the free constant in this equation, represents a y-intercept, and as we see from the graph, your graph crosses your y-axis there. This point is 0, -1. Okay, so moving on, which linear functions do we know in our reality, day-to-day life? Well, one of the functions that you're very familiar with is the distance formula, which is distance equals rate times time, or speed times time. And this is function of t. It depends on t. You input t, right? T is your input. And then you calculate your distance covered based on that input. And this is the rule that you use to calculate your output. You take your time that was given to you, and you're multiplying it by rate. Okay, so here what I wanted to mention is that your functions could be given in different forms, right? So here we have an equation, we have a table of values, and we have a graph. So your functions could be given in any one of these outputs. And you should be able to toggle between those. So given the table, figure out the function. Given the graph, figure out a function equation. Given a function equation, create a table, create a graph, and so forth. So let's dive into it a little bit more. So here's one of the examples from your book, and it talks about Shanghai Maglev train, and it carries passengers comfortably for a 30-kilometer trip from the airport to the subway station in only 8 minutes. So, and that's about 19 miles in only 8 minutes. Okay, Suppose a maglev train travels a long distance and maintains a constant speed of 83 meters per second for a period of time. Once it is 250 meters from the station, how can we analyze the train's distance from the station as a function of time, starting after it already sped up? Because yeah, the rate for one thing about linear functions that we're going to be talking about in a second is that they have constant rate of change. So we have to start once the counting the distance once the train already traveling up to speed. Okay, so here's a table. We have, so this is a tabular form of representation. So when t equals 0 at the beginning of when we start counting time, the train is, so this is your input, time is your input, and distance is going to be your output, right? So when no time lapsed, the train is 250 meters from the station, and then 1 second later, we know that it travels 83 meters per second. So 1 second later, it's 250 plus 83, which will give us 333. And then we do that the next second, one more second passed, and it's 83 meters further away, and so forth. How, looking at this table, how can you tell if that's a linear function? If that's a linear function. So something that we are going to talk about is, or look for, is a constant rate of change. Constant rate of change. Okay. And rate of change is something that you're going to be talking about in your calc classes a lot. So linear functions have constant rate of change. What does that mean? Well, that means that as as long as these increments for the input values are the same. So here, and we're calling those increments delta x. So that's the notation. Little triangle, we read it as delta, and this represents the change in x. Change in x. And this is a delta y, the change in y values, the change in function values. So we have a constant increments, or delta x's are the same, and then the delta y's, or increments of y, increasing or decreasing, they're also the same. In this case, it's 83 meters. So delta x for this table would be 1 all the time, constant, and delta y, or change in y, is also constant, 83. So when we talk about rate of change, so rate of change is delta y divided by delta x. Okay, so for this specific case, it's 83 meters divided by 1 second. So that's a rate of change of the distance. The distance is changing 83 meters per second. It's increasing at the rate 83 meters per second. So this is how it translates. Now, this is your tabular form to represent a linear function. Now, what about the graphical form? So here we have a graphical form, and We see an equation here that represents this particular function. D of t equals 83 times t plus 250. Well, 83 is your coefficient in front of t, and we just saw it a second ago, and this is our rate of change, that in linear functions we call slope. This is your slope of the line, and it's represented by m in that general equation, in that slope-intercept form of the equation. Now let's talk about 250. What is that? Well, we know that it's your b value or your y-intercept, right? This is your y-intercept. But in the context of the problem, what is it? Well, remember that we started measuring distance with 250. So at time 0, when we turn on our clock, or timer, the train was already 250 meters away from the station. So this is your initial value. So the y-intercept, it always represents initial value. So represents initial value, at x equals 0, or in our case, it's t equals 0 when the time starts, when x is 0. That's what this constant, that's its meaning, in the equation when applied to real world problems. Okay, so so we know the y-intercept is 250, and then the line increases at the rate of 83/1. That's the slope, grows very fast. That's why on the y scale, we have basically our units in hundreds. Okay, and one more way to describe our function is just to give the equation straight. So here it says the pressure P in pounds per square inch, PCI, in the diver, on the diver, depends upon her depth below the water surface, D, in feet. This relationship may be modeled by the equation, and here's our equation. And it says basically explain what this equation gives us. Okay, like we said, 14, the b value is our initial value. So what is the initial value? The initial value, since our inputs, first of all, let's identify the inputs and outputs. So the input for this function is d. What is d? That's the depth. All right, and then the output, what's the output? Pressure, or measured in PCIs, right? Pressure. Okay, so then our free term, our B value, is the initial pressure, right? Initial pressure. That's when D, or depth, equals 0. So there is no submersion yet. So that's the initial pressure. So that's the basically pressure, atmospheric pressure. When D equals 0. Okay, now what is the other constant here that we have? Okay, there it is, and that's our m. This is our rate of change. So the rate of change, m, is 0.434 And what is the units that it's measured in? So this is pressure. This is how pressure changing, the rate of change of your output pressure. So it's measured in PCIs. PCIs per and on the bottom you always put the input units. So D is measured in feet. So it's a rate of change of 0.434 PCIs per 1 foot. So that's how fast the pressure is changing as the depth is changing. So that's the meaning of this constant. So this is the end of the intro video, and please go to the next video for more information.